Assalamualaikum warahmatullahi wabarakatuh. I am Nurul Shahira together with Nur Shakira and Siti Nur Amira from Group 2 will be presenting on Chapter 5 Mechanical Properties of Materials. Not to forget to the other members Nurul Natira, Nurzalin Halida as well as Muhammad Muizuddin. Then, I will start my presentation by explaining more about the mechanical properties of material. Mechanical properties are important in understanding and predicting a material's behavior under load. The first one is elasticity. It is the power to revert to its original form after deformation. For example, stretching rubber band. When we stretch rubber band, the shape is changed and after deformation, it will return to its original shape. Secondly, it is plasticity, which is ability to undergo some degree of permanent deformation without rupture or failure. In other words, it cannot return to its original shape even after the deformation. For example, squeezing the rubber ball. Thirdly, ductility. It is a measure of how well a material can be drawn or property of a material which enable it to draw out into thin wires. For example, copper can be drawn into long wires. The fourth one is malleability. It means property of material in which it can be beaten into thin sheet without rupture. For example, blacksmithing. The material was beaten to form a shape. The fifth one is toughness, where amount of energy that can be absorbed by material before failure takes place. As an example, a diamond is very hard, but can be completely smashed with hydraulic press. The last one is strength, which the ability to resist the application of forces like tensile, compressive, or shear without breaking. Tensile strength is the maximum tensile stress a material can withstand without breaking. The formula is tensile equal to F tensile over A. Often, it is not the strength of material that is important to determining the situation in which a material can be used, but the value of the stress at which the material begins to yield. For example, deform. Moving on to the types of stress, which is shear, compression, and tension. Shear is ability to withstand offsets or traverse loads without rupture occurring. Shear stress exists when two parts of material tend to slide across each other. The force can cause the material to bend, slide, or twist. Compression is ability to withstand squeezing loads without being crushed. The adjacent parts of materials tend to press against each other, and this leads to shortening the material. Meanwhile, for tension, it is ability to withstand tensile loads without rupture when material in tension. Tension stress exists when two sections of material on each side of stress plane tend to pull apart and leads to elongate, and it will become thinner and longer. We continue on stress and strain part. Stress is force applied per unit area, also an applied force that tends to deform a body. The formula is stress equal to F over A, which F is force applied and A is area of force application. The unit is Pascal or PSI pound per square inch. Next, strain is change in dimension per unit length. The formula is strain equal to change in length over original length. There is no unit because it is the ratio of change of length to original length. And the next one is tensile test. This test is one of the most basic and common types of mechanical testing. It applies tensile pulling force to a material and measures the specimen's response to the stress. By doing this, tensile tests determine how strong a material is and how much it can elongate. The test was run by using tensile test machine or universal testing machines. Firstly, the ends of the test piece are fixed into grips. Then, the specimen is elongated by the moving crosshead. The force applied to the test specimen is measured by load cell. And lastly, displacement's elongation under load is measured by extensometer. From the tensile test before, we observe the strain stress curve. First, yield strength point. At this point, the material starts to deform plastically, and the permanent plastic deformation occurs after past the yield point. Then, ultimate tensile strength UTS. This point represents the maximum stress that the material can endure before failure. The necking begins at this point. Meanwhile, at breaking strength, the failure of materials takes place. And we will proceed to elastic and plastic deformation. For elastic deformation, it is the object that will return to its original shape when the deformity is removed. For example, before any load is applied on the spring, the shape doesn't change. The shape starts to change when a small load applied by stretching the spring. And it will return back to its original shape when we unload it. Elastic means reversible. Meanwhile, plastic deformation is metal atoms are permanently displaced from original positions. For example, the shape of the tin can doesn't change because there is no load is applied. It changes when small loads applied on it, and when the deformation is removed, the tin can doesn't return to its original shape back. And other than that, under elastic deformation, there is modulus of elasticity or Young's modulus. Young's modulus is stress and strain are linearly related in elastic region. Hooke's law. The higher the bonding strength, the higher the modulus of elasticity. And lastly, Young's modulus comparison. As an example, modulus elasticity of steel is 270 GPa and aluminum is 76 GPa. Based on the data shown, the steel and aluminum are fall in metal alloys category.
Let's talk about yield stress or yield strength. Basically, every materials would begin to experience elastic deformation at first. But once the stress of the material is exceeding on a certain amount, this material will be suffered with plastic deformation. When this switch occurs, the material has reached its yield stress. A structure or component that has plastically deformed may not be capable of functioning as intended. Thus, it is preferable to know the stress level at which plastic deformation begins or when the phenomenon of yield stress happens. Other words, yield strength is an indication of the onset for plastic deformation. According to the stress-strain curve above, the yield strength could be determined on the intersection of the curve with a 0.2% offset. Meanwhile, to obtain the point of yielding is at the initial departure from linearity of the stress-strain curve. After materials experience yielding, the stress necessary to continue the plastic deformation increases to a maximum, and this is where the ultimate tensile strength is occurred. At the stress-strain curve, the term necking would be happen right after the ultimate tensile stress region at the curve had reached, and usually necking region falls under the third stage after the linear elastic and strain hardening regions. If the metal is more ductile, thus more the necking would take place before its failure. Strain hardening, or known as work hardening or cold working, is the process by which the metals are made stronger and harder through permanent deformation. Strain hardening falls on the region at the stress-strain graph, where the metal is strained beyond its yield point, reaching a maximum at the ultimate strength point. Another significant mechanical property is ductility, and in general, the ability of the material to deform under tensile stress. Precisely, ductility is a measure of the degree of plastic deformation that has been sustained at fracture. Ductility also serves the meaning of the amount of elongation that tensile specimen undergoes during testing. The ductility of the material will be higher with the increase of percent elongation. As shown in the graph above, The green curve indicates a larger percentage elongation at failure, meaning this particular material when elongates has high ductility, and for the blue curve implies the contrast. Having small percent elongation leads to lower ductility. Next, toughness is the measurement for the amount of energy in which the material could absorb before to fracture. And from the stress strain graph, this specific fundamental property could be measured and obtained through area under the curve. This method is also known as the work of fracture. Based on the graph above, displays what types of curves will be obtained according to each materials, and the least toughness is unreinforced polymers, whereas the largest toughness is metals. As shown in the figure above are various types of tensile stress strain curves or graphs that will be obtained according to the materials that are being used, and this shall assist in the ability to classify each type of materials respectively. For majority of the polymeric materials, a simple stress strain test is applied for the characterization of polymer. For example, rigid plastics such as polystyrene, polymethyl methacrylate, or polycarbonate could hold out against a good deal of stress, but they won't withstand much elongation before breaking. Flexible plastics like polyethylene and polypropylene are different from rigid plastics in that they don't resist deformation as well, but they tend not to break. If an amorphous polymer has a glass transition temperature or TG below room temperature, that polymer will be an elastomer because it is soft and rubbery at room temperature. Hardness is one of the mechanical measurements and properties in which it measures the resistance of metal to permanent deformation or plastic, or indentation or resistance to scratch. Furthermore, hardness could be an indicator for the wear resistance of material, and the term wear resistance refers to the material's ability to resist materials lost by some mechanical action. Therefore, the wear resistance will be greater the harder the material is. Hardness can be tested by a number of techniques including indentation, scratch, and rebound hardness measurements. But one of the early hardness tests is called the Mohs hardness. This test is basically to assist in identifying the minerals by measuring the ability of the material to scratch with another one of known hardness on the Mohs hardness scale. Indentation is the most commonly used test to determine the hardness of a certain material, and indentation is a notch, cut or dent in something, or even a concave cut into a surface or edge. The indented material could be in a form of ball, cone, or even pyramid, and usually the material is made of a much harder material in comparison with the tested materials. The materials will be considered as soft if the indentation produced were larger and deeper. Apart from that, there are various techniques to measure the indentation hardness of the materials, and examples are Rockwell, Brinell, Vickers, and Knuth.
Alright guys, now I will explain about hardness testing. Basically, the concept of this test is just press the indenter into metal surface, withdraw the indenter, and based on the depth and width of the indentations, we can measure the hardness. Let's all go through types of hardness tests. First, Rockwell hardness test. This test is the most frequently used in the world since it does not require a highly skilled operator to use them, and it is inexpensive, relatively non-destructive, and usually leaving only a small indentations in the material. This hardness test is usually used for larger sample geometries, and there is two types of indenters in Rockwell hardness test, which is first braille indenter, which usually used for ferrous metals that will be indicated by Rockwell C number, and the other one is steel balls that will be used on non-ferrous metals, which will be indicated by Rockwell B number. Next, Vickers hardness test. Vickers is a hardness test for all solid materials, including metallic materials. The Vickers hardness is calculated by measuring the diagonal lengths of an indent in the sample material left by introducing a diamond pyramid indenter with a given load. The diagonals of the indent are measured optically in order to determine the hardness using a table or formula. It is often easier to use than other hardness tests since the required calculations are independent on the size of the indenter. The indenter can also be used for all materials irrespective of hardness. This hardness test is suitable for a wide range of applications including micro hardness testing. Next, the Knoop hardness testing. Knoop is an alternative to the Vickers test in the micro-hardness testing range. It is mainly used to overcome cracking in brittle materials as well as to facilitate the hardness testing of thin layers. The indenter is an asymmetrical pyramidal diamond, and the indent is measured by optically measuring the long diagonal. Careful specimen surface preparation like grading and polishing may be necessary to ensure a well-defined indentations. It is suited for measuring the hardness of small selected specimen regions. What is the advantage of this hardness test? Well, this test is simple, inexpensive, indestructible, and also provide estimation for other mechanical properties. The definitions of failure is a breakdown of an object such as metal, concrete or plastic due to various factors that affect the strength, the stability and chemical compositions of the object's structure. The terms that we will be focused on in these subtopics are fracture, fatigue and creep. So, what is fracture? It is a separation of solid under stress into two or more parts. Basically, the steps in fracture are crack formations and crack propagations, and there are two types of fracture, which is brittle fracture and ductile fracture.
To understand more about these types of fracture, let's take a look at this picture. It shows the classifications on both ductile and brittle fracture. Ductile failure is a type of failure seen in malleable materials characterized by extensive plastic deformations or necking. It usually occurs prior to the actual failure of the material. In ductile failure, there is absorption of massive amounts of energy and slow propagations before the fracture occurs, and it don't break immediately and occur at the most metals, which is not too cold. Meanwhile, brittle failure refers to breakage of material due to a sudden fracture. Usually proceeds along characteristic crystallographic planes called cleavage planes and has rapid crack propagations. It has no appreciable plastic deformations, so they will break at the end of elastic limit. The crack propagations is very fast and break without any warning. This failure usually occurs at ceramics, ice or cold metals.
The stages in ductile failure are necking, formations of microvoids, coalescence of microvoids to form a crack, crack propagation by shear deformations, and lastly, fracture. To make it clear, let's take a look on the example of failure of pipe. In ductile failure, it breaks into one pieces and large deformations. Meanwhile, in brittle, it broke into many pieces and has small deformations.
And now, what is fatigue?
Fatigue failure refers to the fracturing of any given material due to the progressive cracking of its brittle surface under applied stresses of an alternating or cyclic nature. Over time, fatigue failure can lead to safety issues and the loss of critical infrastructure. To make it simple and understandable, fatigue failure is the property of a material to withstand continually varying and alternating loads. Fatigue equal to failure under repeated and constant stress. It causes 90% of mechanical engineering failures. Fatigue failure is brittle-like even in normally ductile materials, thus it's sudden and catastrophic.
The example of fatigue failure is what happened at Oroville Dam, California in 2017. The problem started when a giant hole suddenly opened up in the chute.
The last term to know in this subtopic is creep failure. creep failure is the time-dependent and permanent deformations of a material when subjected to a constant load or stress. These deformations typically occur at elevated temperature, although it may occur under ambient temperature as well. As an example of this creep failure, jet engine turbine rotors and steam generators can experience creep due to increased temperature and stress exposure. At some point, failure may occur. Therefore, the study of creep is very important for those materials which are used at high temperature like components of gas turbines, furnaces, rockets, missiles, and others.
Well, I think that is the end of this chapter. I hope after you watch this video, it will help you to understand more about mechanical properties of materials. Thank you for watching guys, and Assalamualaikum.